Okay, so make sure that when you have come to this slide that you are completely in comfort with all the jargon that was just discussed, things like plane of incidence, how to draw a linearly polarized electromagnetic wave by just indicating the three arrows K, E and H, right, and also understanding what is the notion of parallel and perpendicular polarization. Okay. So, from here on out it is going to be a lot of geometry. Okay. So, let us start okay. So, I have a plane wave okay. So, I am going to demarcate some angles theta I, theta R and theta T, right. So, T stands for transmission, R stands for reflection and I for incident, right. So, I am using H index I, K index I and E index I for the incident quantities, right. So, I am going to use the subscript R for reflected and T for transmitted quantities. Okay. So, remember that this is a purely dielectric media on either side, which means that there are no surface charges or surface currents, right. So, there is no free charges standing at the interface or currents, right. So, in this particular case, what can we say? We cannot expect any new components of magnetic fields to arise, right. So, the only source of magnetic fields, oscillating magnetic fields, is the incident beam itself, right. So, there are no outstanding currents or charges that can create fields by themselves, right. So, the only source of excitation is from the input beam. Okay. So, the way I can draw the reflected wave is that the magnetic field is still oriented outwards, right, it is perpendicular, and in that case automatically the other two vectors get decided. Okay. Similarly, okay. So, please get comfortable in drawing these figures, right. So, remember the E, H and K follow the thumb rule, the axes follow the thumb rule, right. So, this is my x, right. So, the xy plane indicates the boundary, right, and the z axis is going into medium 2, right. All right. So, in this case, if I were to start writing expression, Hi is the easiest vector, it is oriented in the y axis, right. So let's say that I have an incoming plane wave where the magnetic intensity is h naught. So that's the magnitude. Then we have the direction, and then the spatial dependence, right. So this is going to be minus j k dot r. So now what can we say is the k vector? So ki is kx I ex plus k z I ez. Okay, the k vector is in the xz plane. There is no component of the k vector in the y axis. So we only have two components for the k vector. I am demarcating that as kx and kz with the subscript I for the incident, right. So this ki dot r will essentially yield us kx I x plus kz I z. This is my spatial dependence, and then of course we have the e to the j omega t. Okay. So remember that we are still in the realm of solving Maxwell's equations, right, which is linear. So let's not worry about the time dependence. So I'm going to drop off the e to the j omega t in all our subsequent expressions to understand that all of the elements, whether it is the electric field vector or the magnetic field vector, they are all oscillating with the frequency omega, right. So we'll only focus on the first three terms, which is the magnitude, direction and the spatial dependence. Okay. So we've written down the expressions for the magnetic field and the wave vector k. All that's left for the incident field is to write the electric field vector. Okay. So this is an exercise I want you to do. This is simple geometry, but you need to get well versed, right, with this. So remember that if the angle of incidence is theta I, this angle is also theta I. Okay. And based of law of right angles, you can figure out that even this angle is theta I. Okay. So what can you say is kxi? It is simply modulus of k sine theta I. Okay. The component of k that is along the x axis is ki sine theta I. Similarly, kz I is the modulus of k I cos theta I. Okay, so I am basically just representing the k vector using the axes as defined by the boundary, right. So what can we do for the electric field now? So what is the magnitude? It is simply the wave impedance multiplied by the magnetic field intensity, right. So I have my magnitude, but then what is my direction? Okay. So again the electric field vector is in the xz plane. Okay. So I need a unit vector along the direction in which the electric field vector is pointing. Okay. So I can use this using the cosine and sine angles, right. So, a unit vector in the direction of E EI specifically for the incident electric field is quite simply cos theta I Ex, okay, and minus sin theta I Ez, okay. So, you can just take the electric field vector EI, right, and just look at its horizontal and vertical components, right. The vertical component is given by cos theta I and the horizontal component is sin theta I, but it is looking in the minus z direction, right. So, this is a unit vector. Why? Because square root of cosine square theta I plus sin square theta I is 1, right. So, this is my direction. So, cos theta I E x minus sin theta I E z. Okay. As far as the spatial dependence is concerned, it is the same as the magnetic field, right. So, I can just write e to the minus j kx I x plus kz I z. Okay. So, students should be absolutely comfortable with writing down the expressions for the magnetic field vector, the electric field vector and the propagation vector given a plane wave that is randomly oriented. Okay. And eta here I am going to write it with the subscript 1 because eta 1 is the wave impedance in medium 1 and that is given as square root of mu 1 over epsilon 1. Similarly, we can say eta 2 for the plane wave in medium 2 would be square root of mu 2 over epsilon 2. Okay. So, to sort of continue the exercise, the more you do, the easier it becomes, right. So, we are going to start writing HR. Okay. So, remember that we notice that beam that is incident at the dielectric medium, some of it gets reflected and some gets transmitted, right, which means that the field amplitudes get diminished, right. So, only a fraction of the incoming amplitude is going to be transmitted or reflected, right, or reflected and refracted. So, we need necessarily a new amplitude, right. So, we cannot have H naught, but we will call this H naught R. Okay. The orientation is still EY. Okay. But now the spatial dependence is different. Okay. What is the spatial dependence? Okay, so we will look at that. So, KR is again we can say KXR EX plus KZR EZ. Okay, but KXR is essentially still oriented up, right. So, modulus of KR, and now let us look at the angles. Okay, so this is theta r. Okay, similarly this angle is theta r. Okay, so we can use these to essentially get our components. So k r sine theta r alright, modulus of k r sine theta r is my k x r, and what is my k z r? It's modulus of, but this time since the reflected beam is actually going in the minus z direction, right. So, I am going to put a minus sign and say this is cos theta r. Since kzr is negative, what we will do is we will sort of put a minus sign here, right, so that kzr is positive. Okay. I have absorbed that minus sign in writing the kr vector itself. Okay. So, let us write this as minus jkx r times x and e to the plus jkzr z. Okay. So, the minus kzr and the minus j, they multiply to give me plus jkzr z. This is to indicate that the wave is traveling in the minus z direction, in the positive x and minus z, right. Okay. Now, unit vector in direction of ER. Okay. So, we are going to have ER is going to be given by, remember the wave impedance in medium 1, right, it is still eta 1 h 0 r, that is my magnitude. Now, the direction, so we can say that the direction is minus cos theta r Ex, right. So, the electric field is got a component that is facing in the negative x direction and in the negative z direction. So, minus sine theta r Ez. Okay, so we can write that here, minus cosine theta r Ex minus sine theta r Ez. Okay, you might feel that it is going a bit slow, but this is highly critical, right. Remember that these components are the ones that we are going to use to now establish boundary conditions, right. So, remember that the 4 Maxwell's equations gave us 4 boundary conditions that essentially related the parallel and perpendicular components of the electric and magnetic field vectors. Once you write it out correctly, the various components of the electric and magnetic fields, setting up the boundary value condition, right, becomes very straightforward. It is just looking at the right orientations and equating those components. Okay. So, lastly we have H transmitted still in the EY direction out of the plane. Okay. Here we have minus j kxt x and e to the minus j kzt z, okay, because it is propagating in both positive z and positive x, okay. So, the transmitted wave looks sort of very similar to the incident wave, right, in terms of the orientations of the vectors, but the angles can be different, okay. So, what can we write for ET? This time the wave impedance has changed, okay, so keep that in mind. So, eta 2 h0t, okay, and the orientation, don't forget that there is the spatial dependence that comes here, right. For lack of space, I am just only looking at the orientation, but remember that the spatial dependence is there in both the electric and magnetic field vectors, okay, don't forget to include that. So, the orientation, so the unit vector for ET is again cos. So, let us draw the angles. So, we have this being theta t, and so this angle is also theta t, okay. So, we have cos theta t Ex and minus sin theta t Ez, okay. And let us not forget the spatial dependence after, okay. So, it is quite clear that just by knowing the fact that E, H and K are mutually perpendicular to each other, I am able to just write down expressions, right. So, what are all the unknowns here, right. So, assume that H naught is given to you, that is the incident beam. The unknowns here are H0 R, H0 T, right, we do not know those constants. Similarly, theta R and theta T are unknowns. Could I say Kr and Kt are unknowns? No, right. So, remember that we always have this relationship between k and omega. So, we have k1 for a wave vector in medium 1, it should always satisfy this equation. Similarly, a wave vector in medium 2 should satisfy this equation, right. So, the moment you give me epsilon 1 mu 1, epsilon 2 mu 2 and the electromagnetic wave's frequency, I should immediately know what the wave vector magnitude will be, right. So, mod Ki, mod Kr and mod Kt are all known quantities, okay. So, let us call these unknowns and let us write down the known quantities, right. So, H0 is known, eta 1, eta 2 are known, okay. Remember mod Ki, mod Kr and mod Kt are all known quantities, okay. the thetas are unknown, but modulus of the wave vectors are known quantities. Okay. So, we are all set out to understand how we can use the boundary conditions that we learnt last week to identify the unknowns. Okay. Remember, we are not doing solutions to Maxwell's equations, right? Thank God for it. So, the derivation of boundary conditions were from the integral form of the Maxwell's equations, and that has elegantly allowed us to be able to simply map these quantities to each other, relate them and get certain relations, right.